For who? For
what?
us? For us, professor, or just for? I didn't hear you well.
I didn't understand. Sorry, say that again.
I said I didn't hear you well where you were talking. Can you repeat, please?
Yes, I'm saying that soon, maybe next week, you will take an exam, okay, a written exam.
Yeah.
Covering my lectures, and this will not happen this week, not within my scheduled hours. That's all. Okay, that's all I said. I haven't prepared.
Next week, sir.
I don't know. This is it depends on that. Depends on Karim Audia. I will send it to him, and he will organize the exam. So I guess this can be negotiated with him.
Okay.
But I would kind of, I mean, I don't know what your schedule is for the next week. So I guess you and Karim can figure it out.
Yeah. Okay. So.
All right.
Thank you.
Yeah, and I don't know, any other questions?
Excuse me. So the students from IFAR, we are joining now. So I don't know if we will be able to do exams or your exam next week.
It's not, this is something that needs to be determined by whoever is in charge of these things. I'm just in charge of teaching you guys, and all that I know is that I will send Karim Audia a set of questions, and then he will see about examining you guys. So don't ask me how that is going to happen, because I don't know. Okay, but one way or the other, it will have to happen. So someone will have to figure it out, and I'm sure you will be informed in due time.
Hello, sir. Please, my question is, how is the questions going to be like? Are we going to prove the equations, or we'll use the equations to solve questions?
Well, basically, there are, you have to know and understand the content of my lectures. So if I proved an equation in class, you should be able to redo it yourself.
Okay, thank you.
I'm not, like, we didn't do like math exercises of stuff like that. So I don't think I will ask you to do anything much different from what we've done in class, okay?
Okay, thank you.
So that I can pretty much promise. But other than that, whatever has been covered in class, it's fair game, as they say. So. All right, don't worry too much about it. Just a little bit. Okay, here we go. So, what you see on the screen, on the whiteboard, is Navier. They just turned up the heating, so it's really hot in here. This thing is resting on my, sorry, Navier's equation. And so you remember what that means. It means that at every point of a medium, an elastic medium, okay, this equation contains elasticity in it. Remember, to obtain this equation, we had to use a law, Hooke's law, that holds for an elastic medium, that describes elasticity, that describes the behavior of what we call an elastic medium. So this holds for elastic medium, and it holds at every point of an elastic medium. So notice that it contains lambda and mu, which are elastic parameters, and that I don't know if I emphasized it on Monday, but we assume them to be constant in space and time, okay? Which in the real world, it doesn't necessarily need to be the case, but it's a good start, okay, to see what we can understand about a simple medium that has constant parameters, lambda and mu. And we will learn later a bit more about what they mean. And then, so U and is a function of the coordinates, the vector, the position vector x, which means that basically this equation, like I said, it holds at every point of the medium, and things change if you move around in the medium, right? But the equation is still valid. So if you find the U of x and t that solves this equation, you know how the medium in its entirety behaves over time. And F also is a function of space and time. It's a force that causes the displacement within the medium. Or actually, I shouldn't put it that way. It's not necessarily that force that causes the displacement. The displacement can be the consequence also of some initial conditions that perturb the equilibrium state, and as such also initiate some deformation. So F could, in practice, in the real world, it's either weight in the type of problems that one might be faced in seismology. So it could be gravitational attraction weight, or it could be used to represent the source, okay, as alternative mathematical description as opposed to prescribing some initial conditions. But like I said, we prefer the initial conditions approach, which is the same approach that we used for the string. So, and also in the first approximation, it's okay to neglect gravity. So basically, I can get rid of this term and still get a reasonably realistic solution. When I say, why do I neglect gravity? I think that it amounts to assuming that the force, the elastic force that tends to bring the medium back to its equilibrium shape is stronger than gravitational attraction. Okay, those intermolecular forces that I discussed last time, they are more important in determining the behavior, okay, of the medium than gravitation. And we know that that is the case because with this approach we can compute what we call synthetic seismograms. Okay, we can make a prediction of what the motion at the surface of the Earth, at the place where I place my instrument, will be after a certain seismic event, an earthquake or an explosion. So we can make this calculation and we compare that calculation with the data. Okay, we can also make a measurements, and we have many examples that show, nowadays we have many examples that show that to a large extent, whether or not we include the effect of gravity does not have a tremendous effect on our calculations. Okay, so we can do this simplification and we are left with a simpler equation that I'm now going to solve. Okay, so remember this equation is a consequence of Navier's, the more general Navier-Stokes equation that also have force. But if we in addition, Navier-Stokes is basically just a direct consequence of Newton's second law. But if we add to that equation the hypothesis that our medium behaves elastically, so we essentially establish a linear relationship. We hypothesize that there is a linear relationship between tau and u, and that relationship, remember, these are the sort of equations that you might want to know by heart if you want to learn something by heart. So remember, there's what we call Hooke's law. I'm going, just to save space, I'm going to use the small deformation tensor, right? Hooke's law. Then we obtain the Navier's equation. I apologize for insisting on these things, but actually I would like you to even remember in the future that actually historically it happened the other way around. Actually, Navier's equation was discovered before Navier-Stokes. Okay, Navier, long before, well, a few decades before Stokes, he actually Cauchy came up with this equation, modifying a little bit some earlier work by Navier, without basically using the concept of stress, but thinking directly everything in terms of deformation. So he would immediately write surface forces in terms of deformation without establishing Hooke's law, and he obtained directly his equation. Later, it was understood that by introducing a stress tensor, one could write this more general law that is valid independent of rheology. So what is rheology? Rheology is the relation, essentially, rheology is how a medium responds to deformation with stress. So if I say that my medium is not elastic anymore, it's viscoelastic, Navier's equation doesn't hold anymore because Navier's equation only holds if we have elasticity. But Navier-Stokes is still valid. You just have to replace the Hooke's law with another stress deformation, stress displacement relationship. Okay. That was a brief review of last week. Now the trick that you might have seen before, I'm not sure, but that we certainly see again in the future if you do any seismology course, to solve a problem like that is to use a theorem, mathematical theorem that I'm not going to prove because it's complicated and because it would take a lot of time, but well, you can always find material, or I can send you some material if you want a formal proof. It's called the Helmholtz Theorem. Helmholtz was a very important physicist, also in the 19th century, a German physicist who, well, he did a lot of stuff, and he was also a great communicator. He wrote some really good books for the general public, but he was a very important acoustician on most of the things. And anyway, he came out with this theorem that said that for any vector field F, well, let's call it, it's a vector, so let's call it V. V. There exists a scalar field phi. Yeah, V that is a function of position in space, okay? There exists, okay? This means there exists. You can find a scalar function phi, also function of x, and a vector function psi, such that V can be written as the gradient of phi plus the kern of psi. Okay, the curl of a vector is essentially the complex expression that you obtain if you take the vector product of nabla with the vector in question, okay? So I don't have time to do like a full math review, but if you know what a determinant is, one way to think about it is that if you have, like here, I think you have in the first row, you have the 3 unit vector that are oriented like the 3 Cartesian axes. In the second row, you have the 3 spatial derivatives with respect to the same 3 Cartesian axes. And in the third row, you have the 3 components of the vector. Okay, so maybe you remember these things, maybe not. Don't worry too much. Just take an hour this weekend to review your math, the curl and the vector product. And I think I sent you already a chapter in Hildebrand with a review of vectors. So did I? I don't remember. I'm not sure anymore. Let me actually check.
Yeah, you said.
I did. Okay, good. So
yeah.
I think that, yeah, vector analysis, yes. So you have everything in there. And there, I mean, everybody has their favorite books, right? But that's one place where you can pick, where you can look. Okay, so you can see this. The full significance of this thing will become clear over time if you keep thinking about this stuff. But you can think of this as a funny and potentially useful property of the nabla operator. Okay, that V no matter what vector field, if something is a vector, you must be able, you are necessarily able to write it as a combination of the gradient of something and the curl of something else. Okay, and let's see why this strange mathematical result is useful for us. Well, it's useful because it turns out that if we now allow me to delete all these. So it's useful because well, if Helmholtz is right, and Helmholtz is right, then we can apply his theorem to our unknown vector field U that we are trying to determine. Okay, we are back to the situation where we just have to solve a mathematical problem. We just have to solve a differential equation. Okay, there's only one unknown here, U. So now there aren't so many simplifications we need to make. We just have to solve this mathematically. So, okay, so let's apply Helmholtz idea to our vector field U. And so let's write it as a combination of two unknown functions, a scalar phi and vector psi, which stand together with U in this relationship. And let's substitute this expression in the above equation. So now you have to be a bit patient with me, but I think it's useful at least once in a lifetime to work this out. So let's try. I try to go quickly through this, but you will revise it later. So, you just have to do it. Okay, divergence of U becomes the divergence of the whole thing here, plus mu Laplacian of the whole thing equals rho times the second time derivative of the whole thing. So there's one thing that's cool here. We can use a mathematical result, another property of the nabla that you, if you don't believe it, you can read the Hildebrand chapter, which probably gives a proof of these kind of things. The divergence of curl is always zero. Doesn't matter what psi is. If you take the divergence of the curl of something, it goes to zero. It's because of how the nabla works, and it's not so hard to prove it, but we don't have time to do all these things. So this goes already. Small but not insignificant simplification. So
Sure.
Yes.
I didn't understand. You said why it's 0?
Because the divergence of a curl is always 0.
Okay.
Let's see, if you look in the Hildebrand book, I don't know if there's a proof there, but I can send you another chapter. Let's see. Yeah. So it's so if you look at page 278 of Hildebrand, you have a whole bunch of useful properties, and one is 74G is the one I'm using now. Okay, so I don't know if he gives a proof or if it's an exercise, but I think if you read that chapter, you have all the elements you need to convince yourself. Okay?
Okay, sir.
Good, thank you. So, but like I said, it's not physics, okay? Like it doesn't depend on the physics of what psi is. It's just an algebraic consequences of that. If you just write that, if you just work it out, the formula of the divergence of the curl, you see it just has to be 0. Okay, so now so here I'm left with lambda plus mu. Here I have the divergence of the graph is the Laplacian, again, by definition. So I'm left with the graph of the Laplacian of phi. I don't notice that I don't underline the nabla when I take the Laplacian to remind myself that that's not a vector anymore. The Laplacian of a scalar is a scalar. The Laplacian of a vector is still a vector, but not a tensor. Plus mu, and here I'm going to play a little trick, but again, these are things that are okay. You can invert the order of derivation here. So instead of taking the Laplacian of the gradient, you take the gradient of the Laplacian. And then I have same game here, mu times the curl of the Laplacian of psi, which is a vector because it's a Laplacian of a vector. And on the left-hand side, I'm just gonna replace, I'm just gonna use a new symbol here. Please be patient, but I'm running out of space. So if each dot on top of anything represents one derivation with respect to time. So phi with 2 dots on top is the second time derivative of phi. The same for psi. It's just a way to not run out of space on the whiteboard. Okay, so now, now I notice that all these can be compacted to lambda plus 2 mu gradient of Laplacian phi. and then I'm going to bring to the left-hand side everything that depends on, that contains phi. I'm going to bring it together. So let's do things nicely. And then same thing here for psi, mu times the kern of the Laplacian of psi minus rho kern of psi second time derivative, and all of that has to equal 0. Okay. Okay, so now for well, let's write it while you think about what I've done. I write it again. Here I made a little mistake. Okay, the square bracket should have been here. No. Never mind. It was right. Okay, so lambda plus 2 mu. Yeah, I'm going to divide everything by rho. Grad Laplacian phi minus grad phi double dot, and then plus the kern of Laplacian psi, no, mu over rho Laplacian psi minus psi I should underline 0 as well, because it's a vector, okay? These are really 3 equations that I'm writing simultaneously. So a sufficient condition for this equation to be verified is that each of the 2 terms in square brackets is equal to 0 by itself. It's not, I can't prove, or I'm not proving, I don't need to prove that it's a necessary condition, but it is certainly a sufficient condition. Okay, if each of the 2 terms in square bracket is 0, then we are happy. So that's a strategy that we can follow to find a complete solution, general solution, sorry, for this differential equation. Okay, so And actually, allow me also to do something that I forgot about. Just like here, I put the curl out of the square brackets. I can also pull the gradient out of square brackets here. And again, if this guy within square bracket is 0 and this guy within the square brackets is 0, then I have in principle a solution. To the differential equation. So I'm going to write the two equations that I have obtained in this way. And equation number 2 Okay, notice that equation number 1 actually is a scalar equation. Everything is scalar in here. All the vectorial part of this equation we pulled out by pulling the gradient out of the square brackets. And now I'm just saying, okay, if the argument of this guy, of this gradient is 0, then the gradient for sure is going to be 0 too. So I'm going to try to look for solutions to see if I can find solutions that satisfy these. And if I can, then maybe that could be enough to give me a general solution for the equation of motion. And same thing here, but this is still vectorial though. Okay, this is still a vector equation. So we have 4 equations really here. One scalar equation in phi and 3 scalar equation for the 3 components of the vector psi. Okay, so here if you wanted to write it in scalar form, all you have to do is add an index to remind yourself that there are 3 different components and the same equation must hold for components 1, 2, and 3, which are the components with respect to the XYZ Cartesian axis. Okay, so this was fast and not so easy, but if you take a moment to look at what we obtained, and don't worry too much if you didn't follow all the algebra, right? It's cumbersome, but you just need some patience to redo it by yourself. But look at what we obtained. This is something that you should begin to be familiar with. We've seen that equation already in 2 different contexts, okay? We've seen it for the string, where the problem was 1D. So I didn't have a Laplacian here. I had just a derivative with respect to the 1 coordinate that I was using. And we've seen it for the gas, where I had exactly this equation. And remember, one of you said, when we were talking about the gas, one of you said, why doesn't that equation hold in a solid or something like that? I don't remember that. It does, actually. See, if you just take one part of the solution, if you just take this part of the elastic wave solution, that obeys the exact same equation as pressure in a gas, except that doesn't fully describe the deformation of the medium, because if we want a realistic seismogram, we also have to compute that part. Okay, but one part of the seismogram, one contribution to the seismogram has to obey exactly this equation. This is not the same thing as there's more information here than that P0 over rho or P0 over rho that we had in the case of a gas without shearing, because here you have these two elastic parameters that come from Hooke's law, which is the Hooke's law for an elastic solid. Okay, so we have two parameters, not just one, but they are combined together here. You understand that this, if this is the wave equation, this is the square velocity at which those waves will propagate, right? Do you have any questions? Take a minute to think about all this stuff. Basically, there's a lot of math, but
So,
yes.
the equation before writing equation 1 and 2.
Yeah.
Did you divide through by nabla?
Did I derive it?
Did you divide through by nabla before writing equation 1 and 2? This equation.
I divided by rho. Oh, no, I mean, nabla is not something that you derive, that you divide by, okay? Nabla is like a derivative, so you can't divide by a derivative, right? Nabla is a bunch of derivatives.
Okay.
So what I did is simpler. I just said, if this is 0, its gradient has to be 0 as well.
Okay.
Which is not necessary and sufficient, okay, but is still sufficient, a sufficient condition. Which
Okay,
means, since my goal is to solve the ODE, which means if phi satisfies that, then phi is a solution of the differential equation. But be careful about the concept of nabla, okay? Nabla is basically, nabla, it means it's just a compact way of saying I'm going to differentiate. I differentiate with respect to, I differentiate the argument with respect to the 3 Cartesian coordinates.
Yes.
And I put the result in a vector, in the 3 components of a vector. So you cannot just happily divide by this guy. That's not allowed. Okay.
Okay, sir.
Thank you. Anything else?
But sir,
Yes.
if we consider the nabla of the scalar one, the first equation,
Yeah.
it means that this scalar is constant, no?
Phi.
Yeah.
Why should it be constant?
Because its derivative, it's 0. It's null.
No, this is the sum
from the second equation.
In the second equation, there's no phi.
No, sir, I mean, when you said that the gradient of this is 0, we consider the gradient of this is 0.
I never said that the gradient is 0, though. Did I say that the gradient of phi was 0?
Not phi, all the equation. Ah, you said not
Yeah,
phi.
so
Yeah. Okay, I understand. Okay.
thank you.
Okay.
Of course, if phi is 0, that's a solution too, but it's not the only, it's not a very interesting solution. If nothing moves, we stay in the equilibrium situation. That's allowed, but that's not, that doesn't help us understand earthquakes. Okay, any other doubt?
So,
Yeah.
sorry, sir. I don't understand why napla napla time c equals 0.
Say it again. You don't understand why nabla times what?
I mean why napla not bracket napla time c by equal 0.
So it's this equation that you don't like?
No.
The one before.
Under. Yes.
This one.
No, before.
Ah, that one.
Yes.
Yeah. So so basically, you're right to not understand
because
it.
I mean because the nabla time c the result is the vector, and nabla dot bracket nabla time c the result is the vectors y the result is 0. I mean nabla times c is 0. But the napra is a vector, so why napra dot the bracket napra times c is 0? I don't understand. You can write it.
Yeah, I hope I understood your question. Let's see. I show you the way what I think. So basically, what I'm saying here, first of all, okay, here we have, so now that I could expand this to be the gradient of the divergence times the gradient of phi, that gives me the Laplacian of phi, plus the divergence of the curve of psi. Okay, so this is just, we are focusing on this term here. All right, stop me if something is not clear.
Okay.
So now, basically, what I would like you to do later as an exercise is to do the following. Okay, you have all these can be written as such: d over d x1, comma d over d x2, comma d over d x3. That's a vector. Dot product, the curl of psi, which is given by this formula, the determinant of x1, x2, x3. These are three unit vector that are pointing in the directions of the corresponding Cartesian axis. And then psi1, psi2, psi 3. So I'm just telling you that no matter what psi is, if you do this operation, this is going to give you 0. Okay, so don't make me do this now, because it will take some time, and I don't have enough time. But you do it as an exercise, and if it doesn't work, then I have to do it. Yes.
Okay, sir.
Does it answer your question within? Okay. Okay. Anything else? So now I would like you to realize that what we have here is a wave equation that we have learned a little bit about. And remember, you know, in a gas, remember that we used to have the same equation, except that here we had the ratio of P0 over rho times grad P minus the second time derivative of P. Okay, so that's what I was beginning to say a minute ago. It's really the same math, except that phi is not pressure, okay? Phi, I shouldn't have deleted the Helmholtz formula. Phi is just something that controls part of the displacement. We'll see in a second what that is really phenomenologically, but bear with me for a second. So if you should remember that this term in the fluid case, and also in the case of the string, you know, this part of the wave equation is the velocity. It's a velocity of propagation, because remember, the solution of this guy is a function of the type, I hope I get it right, something like that. Okay, so the square root of lambda plus 2 mu over rho is velocity. And maybe this, to some of you, might already ring a bell. Here you have another time the wave equation, except that this part propagates with a velocity mu over rho, square root of mu over rho. Remember that, well, maybe I never say it explicitly, but the way Hooke's law works, lambda and mu are constant, well, are positive constant, okay? So both, rho is also a positive constant because of the physics, you know, that it's a mass density. So this guy is a real number. And this guy here, because lambda is positive, will be always bigger than this guy here. So this part of the displacement propagates faster. And the second part, the current of psi, is slower in terms of propagation, not in terms of how quickly the mass will oscillate. That's a different story, but in terms of how quickly it propagates. Okay, now there's another thing I want you to notice, and that, you know, we've been talking about this divergence of the curve, right? So if I take the divergence of the displacement, I get the divergence of the gradient of phi plus 0, because the divergence of the curl is 0. So that's another way of saying that this contribution to the displacement is divergence free. But what does that mean physically? Remember, and I insisted quite a bit on that, that the divergence of the displacement is proportional, is a measure of the relative change in volume. So if something, if you, a displacement that has no divergence, that has 0 divergence, it can only, it involves no change in pressure, right? It doesn't compress or expand the medium, so it can only be some kind of shearing. So this, basically, this part is entirely compressional, and this is entirely shearing. You can also, if you are familiar with the gradient, which may be in another, it's probably good in a course like that for you to, since I didn't spend so much time on it, but maybe really do some very careful reading, studying of the properties of the nabla of the gradient. Because one property that's also very important is that the gradient points in the direction of maximum change. Okay, so if phi is a spherical wave, which typically it will be if you have a simple source, like if you have a point source. So, but in any case, phi propagates more or less as a spherical wave, and the gradient points in the direction of propagation. You can imagine basically that what you have, you know, it's a typical compressional wave. It's a compression and expansion along the direction of propagation. Okay, so you see where I'm trying to get. We have this first term here that involves a compression expansion along the direction of propagation, and that is faster. It propagates with a velocity square root of lambda plus 2 mu over rho. This guy here, it involves only shearing, no compression, no expansion, and it's slower. it propagates at a velocity of only square root of mu over rho. It's obvious this is smaller than square root of lambda plus 2 mu over rho. Remember, again, these are all positive numbers. So if you've taken any seismology before, at this point, you might have guessed that this is the P wave and this is the S wave. Okay? And if you haven't taken any seismology before, it doesn't matter at all, because you've learned pretty much everything you need to learn in these last few minutes about P and S waves, okay? The P wave is a compressional wave where by compression I mean a displacement that's always in the direction of propagation that doesn't involve shearing. And it's faster. It's really, by construction, it's necessarily always faster than the S wave, which is lower, and it involves only shearing without any change in volume. Also, I want to insist again on this other point. What's a fluid? A fluid is an elastic medium without shearing. Okay, it's still elastic, but it does. You can also have a non-elastic fluid. But the fluid, as we studied last week, it's elastic but has no shearing. That's what defines the fluid. So it's not surprising that the exact same equation describes how pressure behaves in such a fluid, how a disturbance in pressure propagates. Okay, and that's also why, if you're, like I was saying a couple of lectures ago, if one is only interested in P waves, if you just look at the P wave portion of a seismogram, you can use the theory of acoustic media, of media that have no shearing, also in seismology. Okay, what do I mean only interested in P wave? Well, I in the back of my mind, I don't know if that's the same for you, but I'm starting to think about typically how a seismogram looks like, okay? Typically, for reasons that now are beginning to become clear to you, it's usually possible, without much effort, to distinguish what we call the P and S phases, okay? If you're very close to the source, it's difficult because you don't have enough time for the different velocities to play the role, and the two peaks are still very close to one another. But of course, the velocity being different, as the observer moves to a larger distance from the epicenter, the two phases become more and more separated in time. Okay, remember, in a seismogram, the horizontal axis is time always, of course. Okay, and this can be u, the displacement. Let's say it's a vertical displacement, for example, u3. So, yeah. So, and then there's a surface waves, but we still haven't talked about surface waves because so far we've been working with an infinite homogeneous medium with no boundary conditions. Questions? Notice that you have you know, people measure the velocity, well, the arrival time, okay? If you are, when you have seismograms like that, okay? When you see a peak like that, you say, okay, there's been an earthquake somewhere. So you can take, you've seen probably these things before, you can take a seismogram like that from a few stations, and by triangulation, you can figure out where the epicenter is, right? That's a fairly easy thing to do by measuring essentially the difference in arrival time at a bunch of different stations. You can figure out more or less where the epicenter has to be. It's a really just a geometry problem. Once that is done, you can measure the travel time between the epicenter and each station. And by dividing time and distance together, or distance by time, since you know where the epicenter is, and of course you know where your station is, so you can calculate the distance. And if you divide distance by travel time, you get an estimate for the seismic velocity. So in principle, you could use it to determine the parameters that describe what we call the elastic parameters of the Earth, or the parameters that describe the elastic behavior of the Earth. So, you know, it's the kind of things that you guys are supposed to learn to do, because, you know, if you look for oil, for example, you know that oil has certain properties that would result in certain values of velocity and so on and so forth. If you look for coal, if you look for any sort of resources, or maybe if you just want to find out how thick the crust of the Earth is, or maybe if you want to do global seismology, you want to study if there are heterogeneities deep inside the Earth, how irregular is the surface of the Earth's core, of how deep subductions sink in the mantle, and so on and so forth. But there's a big problem here, that even if we measure about P and S, here we have three unknown parameters: density, and then the two elastic parameters, lambda and mu. So this has been old, ancient, I would say, problem in seismology, that seismology alone is not enough to really determine the composition of the interior of the Earth. We can map, if you measure a lot of earthquakes from a lot of instruments, you can, and you will learn that later, but you can use techniques to map, to make three-dimensional images of the interior of the Earth based on this result here. But you can never disentangle velocity from density, which makes it hard then to constrain the thermal and chemical structure of the Earth. But I'm really going ahead of myself. It's more like to give you some time to think about these results. Do you have any questions? Good. So the last topic on which I would like to touch with you guys is surface waves, okay? Which, unless you're very close to the source, are the most prominent part of the seismogram. I will, what I will do, I will probably do it on Friday, but I will go back again, you know, we do the same thing. We find a solution for the Navier equation that also satisfies a boundary condition. The boundary condition is that we will think of the Earth as a half space, okay? So under our feet, we just have an infinite medium that goes forever. And then there's a free surface, which is the surface that we walk on, that is free of stresses, meaning that there is nothing on our side of that surface that can stop the Earth from oscillating around. There is the atmosphere, to be honest, but the atmosphere is not really enough. It's not coupled well enough. It doesn't have the means to stop these very strong seismic forces from setting the surface of the Earth in motion, okay? So we will solve Navier's equation again, imposing a free surface condition. Free surface meaning free of stresses. Before I do that, I want to make some general considerations about surface waves. So, if this is the Earth, okay, imagine we have an epicenter that is at some depth within the Earth, and near that epicenter, okay, before the signal, before the wave makes it to the outer surface of the Earth, basically we only see P and S waves. Okay, if we are observing the propagation of the wave before it emerges at the surface, before it interacts with the free surface, the math that I've done so far is perfectly valid, assuming, of course, in the first approximation that the Earth has uniform lambda, mu, and rho. It's a uniform medium. So if we make that assumption, the math I've done so far, it's perfect until we interact with the free surface. You see just the P and S waves. P and S waves. The moment you start interacting with the surface, you will have a surface wave. And I do the math later. But I'm just telling you now, phenomenologically, the surface wave is something, a disturbance that propagates along the surface. Meaning, if you deploy a recording instrument, if you are able to deploy an instrument at some depth under the surface, we would not see the surface wave. At some large depth, of course. When I say along the surface, I mean along the first at least few kilometers near the surface. And how deep a surface wave sample actually depends on its frequency. So think first of a surface wave of relatively high frequency. And by high frequency in seismology, I mean always around 1 Hertz. So in seismology, that's high frequency. It's very low frequency for a human being because we can't hear anything below like 30 or 40 Hertz. So 1 Hertz is not something that we can hear as a sound. But anyway, so a surface wave at 1 Hertz is high frequency, very high frequency. And typically, it's easier to measure them at lower frequency. So that would be would stick really very, very close to the surface, maybe a kilometer, maybe a few kilometers. And if you could sit like 10 or 20 kilometers below the surface, you would not feel the surface wave at all. Now, if you lower the frequency, if you increase the period of oscillation and therefore the wavelength of this guy, then you would also, in principle, be able to feel this wave at a larger depth. Okay, so how deep the wave samples depends on the frequency. The lower the frequency, it's kind of intuitive actually, okay? The lower the frequency, you have like a bigger thing. You have to move more mass at the same time. And not only you get a larger wavelength horizontally, but also you sample at a larger depth. Okay, if you're in trouble, if this sounds abstract, for me it's helpful to think in terms of sound. Okay, if you want, I don't know if you like, if you ever notice the difference, if you like to listen to music, if you ever notice a difference between a woofer and a tweeter, okay? The tweeter is the speaker for the high frequency, it's small, okay? And the woofer, it's the speaker for the low frequency that's got to be big, because to create a large wavelength thing, ultimately you have to move more mass, okay? So in surface waves span a very broad range of frequencies, okay, compared to P and S waves, which are just, P and S waves are kind of like a small impulse, but a surface wave, it's like this big thing that lasts for a while, and in it you have all these different frequencies, and the tweeter, you know, it's like the part of the surface waves that is stuck to the surface, but then there's also the woofer, that there's also this long period, low frequency surface waves that samples to very large depths. When you feel an earthquake, I guess it depends really where you are. Like if you are near the epicenter, like there's not enough time for all these phases. In seismology, we call phase. It's really not a good word from the mathematics point of view. It's not very rigorous because of the meaning that phase has in Fourier transform theory and in complex number theory, but it doesn't matter. In seismology, we call this the P phase, the S phase. So all these phase, and then you have the surface wave phases. So if you're close to the epicenter, there's not enough time for this wave train to separate. And so you basically feel everything at the same time. If you're farther away, you probably feel the surface wave more than anything else. So I want to explain why, and because I think it's a useful concept to think about. Yeah. So let's go back to this situation here. Let's think of the body. Let's think of the body wave that propagates. Okay, this is say a P wave or an S wave. Imagine you set off an explosion or the earthquake occurs, and these body waves, they propagate as spherical waves. Okay, the energy propagates away from the source. I think we went through a thought exercise like that at the very beginning of this course, so that's good. So think of, you know, this is a two-dimensional section, obviously. So think of each of these curves here as a section through a sphere that really is the true wavefront of this thing. So energy is, as this impulse propagates away, energy gets distributed over a broader area, okay? Which means that if you sit here, even in the absence of an elastic attenuation, just by spreading, geometrical spreading of the energy, you will experience a much weaker oscillation, a much weaker displacement than if you were close to the epicenter, obviously. Even, I insist, even if energy was perfectly conserved, even in the absence of dissipation. So now, for the surface wave, you have exactly the same phenomenon, of course. But the surface wave, it's a two-dimensional thing. So instead of being spread over a surface whose area is it's the area of a sphere, which I don't remember, but it goes like r squared, okay, where r is this distance. So if r is the distance from the epicenter, the geometrical spreading is proportional to 1 over r squared. The total energy is divided by something, some constant, times r squared, 1 over r squared. But the surface wave is distributed not over a surface, but over a circumference. And so the geometrical spreading for a surface wave is just 1 over r. So that means that the it takes a longer distance to decrease the surface wave energy as opposed to the body wave energy, okay? Which means that if you are at some distance, and I think we are talking, about a few hundreds kilometers, okay, that orders of magnitude. So if you are within 100, 200 kilometers from the epicenter, for sure, you will feel the body wave probably as much as the surface wave, maybe even more. But if you are farther away, at some point the surface wave becomes dominant. Then of course you don't feel anything anymore, but the instruments still feel it. For what we call teleseismic events that are at distance of several thousand kilometers, then tens of thousand kilometers, I would say, then you will, the instrument will be dominated by surface waves. Okay, so so what we did so far, really, it was to prove that mathematically, physically, mathematically, that in an elastic medium, inevitably, you will observe a P and a net, what we now define, what we now call P and S wave. We've seen mathematically what they are, and I insist on the fact that they are related to compression and shearing, of course. One important point also to take home with you is that if you don't inject some sort of shearing in the system, you also won't observe any S wave in your data. To observe a shear wave, you have to have some shearing in your forcing term or in your initial conditions, okay? So, for example, one way to tell an explosion from an earthquake in principle is to compare the amount of compression and of shearing that we see in the data. You know that this is a big deal in the history of seismology, because seismology in the last century, to a large extent, has been funded because people were afraid of nuclear bombs, and people in the US would want to know if the Russians were doing nuclear tests and the other way around. So there are organizations still today. There is one organization in particular, the Comprehensive Test Ban Treaty Organization, that is there to be able to use seismic data to monitor nuclear explosions. So nuclear tests worldwide. So that's the kind of thing that they would be looking for. So we've learned to distinguish P and S waves. We learned what they are, and we started talking about surface waves. On Friday, I try to do a bit of the math behind surface waves, and then after that, I'll say goodbye and leave you to my other colleagues. Okay, it's a good time to leave. But if you have any questions, go ahead. If not, I see you on Friday. Okay. See you soon. Thank you very much. Have a good day.
Goodbye, sir.
Bye, bye, bye. Ciao.